Now we need to look at another application of integration, which is volume. Now this is going to get a little tricky in that we're working with calculus in two dimensions. We have the y-axis and we have the x-axis. But volume is a three-dimensional measurement. So we're limited in the amount of volume we can find using two-dimensional calculus. The next step after calculus 2 is to jump to calculus 3. We're still a ways from that. But the jump from calculus 2 to calculus 3 is you go from calculus in 2 dimensions to calculus in 3 dimensions. And once you're in 3 dimensions, it's much easier to calculate volume, or to talk about more complex volumes, I should say. So right now, the volumes we're going to stick to in calculus 2 are what we're going to call volumes of revolution. And a volume of revolution is essentially if you took a two-dimensional figure, let's say something like this, and I look at this little hump here, and that's a two-dimensional figure, and I rotated that 360 degrees around, say, some axis. And so this whole thing is going to spin around this way and come down here, and I'm going to get sort of this shape going on here. This will look kind of like a football. Okay, I could find the volume of that football by knowing the area of the two-dimensional figure I started with. Here are some fairly common figures that are created through this revolution process. Now, in order to find the volume, there's three primary ways we do this. One is called the disk method, another is called the washer method, and a third is called the shell method. The disk and the washer method are fairly similar, and we start off with those. And then we introduce the shell method, which gives us more flexibility in the way we can set up our integrals in order to calculate the volume of revolution. But you could see how all of these figures, your very common figures like your piston or your bottle or your funnel, these could all be created by taking a two-dimensional figure and rotating it 360 degrees around some particular axis. You can see the axis line in each one of these figures for the rotation. Okay? So we'll start with the disk method. And once we get through that, we'll jump to washer method in this video. And the following video will be about the shell method. So in order to talk about the disk method, we need to talk about the most basic element, which is a disk. And so the idea here is if we were to take a rectangle, let's say look at this picture right here, and we were to spin that rectangle around this axis of revolution that the rectangle is sitting right on, okay, that rectangle is sitting right on that axis of revolution. And if we were to spin around that axis of revolution, we would create this disk. Okay, you can see the rectangle still sitting right here. So spin it out, around, and back around again. All right. So you can see how this two-dimensional figure here could create this three-dimensional disk. Let me get rid of some of this. Now, how could we use the area of the rectangle to give us the volume of the disk? Well, the rectangle has two measurements. You have this height, which we'll call R, and you have the width, which we're going to call W. And in that case, for the disk, R is the radius of this disk, and width is the thickness of the disk. And so the disk is basically just a cylinder turned on its side, and the volume of the cylinder should be the area of the base, so the area of the circle times the thickness, which is the width. Area of the circle is pi r squared, so if we use pi r squared W, that should give us the volume of the disk. So you can see how the measurements of the rectangle can help get the volume of the disk. All right. Now, how does that then translate to a whole volume of a figure? Well, let's look at this picture here. Let's say I have this curve, and I get this area that we're looking at in terms of this blue curve. And I rotate that area 360 degrees around this axis that it's sitting on. What figure I would get would be this blue figure here that kind of looks like a Hershey Kiss or something like that turned on its side. I can find that volume with a series of disks. Okay? So if I looked at a bunch of disks that made up, or at least would estimate this volume, say these disks right here, I could get a good approximation of what the volume of this would be. Well, how would I get all those disks? I would get those disks by going back to my area. And what I would do is I would place my rectangles that I would use to calculate the area in here. So I have these rectangles here. And I would spin each one of those rectangles around. And each one of those rectangles spun around would give me each one of these rectangles. Okay. Now, let's think about this area for a second. In order to calculate that area, we did it with an integral. But we originally did it with a limit. And the limit we used was the limit as n goes to infinity of the sum of f of x times delta x. Now, I'm abbreviating some of this, but generally this was what the limit was. What we did was we found the area of the rectangle, which was the height times the width. Remember, delta x represented the width, and delta x was calculated using this b minus a over n. So we had the width, we had the height, which we're going to call, in this case, r, and this gave us the area of one rectangle. Then what we did is we added all those rectangles up. And this gave us an approximation of this area. Essentially adding all these rectangles up, we saw in Calc 1 that that was an approximation of the area, but it was not the exact area, right? So then the trick was to get to the exact area, and that's where the limit comes in. If we let the number of rectangles, which n represents the number of subdivisions, or the number of rectangles, if we let that number of rectangles go to infinity, our error would shrink down. And if our error shrinks down, we go from an estimate of the area to the actual area. So that's the area. Now, how do we take that and then put that into volume? Well, let me get rid of some of this mess here. So if we could calculate the volume of all those disks added together, that would give us the approximation, which would essentially be equivalent to this step. And then if we took the limit of that as n went to infinity, which would be the number of subdivisions, right? It would be the number of rectangles, which would would also be the number of disks, right? Because each rectangle creates a disk. So if we could figure out how to find the volume of this, then let n go to infinity for that volume, we would be able to come up with the actual volume. So the volume of all the disks. Well, the volume of one disk, we said, is calculated using this formula. Now, r is the height of the rectangle. Now, there's not just one rectangle here, right? There are multiple rectangles, but each rectangle's height is based off of the function value, this function of x. We'll call it r of x. So if we take pi times r of x squared times the width, delta x being the width, that should give us the volume of one disk. Okay, one disk. But then we have to add all those disks up. Now the reason why pi is on the outside of the summation is pi is a constant multiple, so pi can come out. So what we have right here is essentially the same idea as what we had here. Here we're adding up all our rectangles. Here we're adding up all our disks. So then the last step that we need to do is take the limit as n goes to infinity. And if we take the limit as n goes to infinity of this, that should give us the actual volume. Now, we got to think about how integrals come into play. Well, this was the exact definition. I have a lot going on here, but this was the exact definition of a single integral using a definite integral. Well, this isn't really any different here. The only real difference between what I'm looking at down here and what I had up here is this is f of x, and this is r of x squared. Other than that, they're exactly the same. I mean, pi is here, but pi is a constant multiple. It can always be pulled out. So if this was, if we used an integral to define this, then this should be an integral just as well. And so that's how we're going to calculate a volume using this disk method. And so these three pictures here show you how we go from one estimate to a little bit better estimate to a little bit better estimate by increasing the number of disks, which really is increasing the number of rectangles, which is something you would have seen in Calc 1. So I know that was a lot, but your background in Calculus 1 and area should have definitely made that a little bit easier. In the long run, here's essentially the two formulas we have for using the disk method when it comes to finding volumes of revolution using that method. They're the same formula. One is just in terms of x, the other's in terms of y. It really depends on what kind of rectangles you were using. If you have an axis of revolution that's horizontal, your rectangle would be vertical. And if your rectangle is vertical, we integrate with respect to x. Okay? If you have an axis of revolution that's vertical, your rectangle would then be horizontal. Again, because we're going to spin around that. We're going to spin around that. And if your rectangle is horizontal, you would integrate with respect to y. I don't like looking at the axis of revolution to determine what variable I should be working with. I like to look at the rectangles that I place into my picture to decide. Vertical rectangles, x, horizontal rectangles, y. And the reason being is we're going to have three methods total. And each method is a little different, but the one thing that's consistent with all of them is the type of rectangle that you place into the picture determines the type of integration you're going to do, x or y. And that goes all the way back to area as well. So other than that, this is the formula for the disk method. R represents the height of your rectangle. That's your R in the formula, whether it's this way or whether it's this way. Pi is just a constant, and the A to B here for the integration represents the total width, and whether that's a width on the x-axis or a width on the y-axis is to be determined based off of how you set up your rectangles. So other than that, it's pretty simple. There's not a whole lot to the formula. The key is getting used to using it. So here's an example. Find the volume of f of x equals the square root of sine x, the solid formed by revolving that region, bounded by the graphs of the x-axis between 0 and pi about the x-axis. So this is what the graph of the sine function would look like between 0 and pi. What would happen is, if I extended this out, here would be 2 pi, and then I would get another hump, and then here would be 4 pi, and I get another hump, and in between there would be nothing. Because your sine function has this curve to it, right? And it's positive between 0 and pi, and it's negative between pi and 2 pi. Well, the problem with it being negative is now I'm taking the square root of the sine. And you can't take the square root of a negative without traveling into the imaginary numbers. So what we basically say is that this essentially would have to go away, and only these values can be in the domain of that function, and what we get is just this hump. And it's not quite the same curve that we had before. It's a little bit more rounded curve than the sine curve because of the square root. But it still maxes out at 1. All right, anyway, we don't need all that. We only need this portion because we only need it between 0 and pi. So then we're going to rotate that around the x-axis. So this is going to come down here, and we're going to get this volume. Okay. So if we're going to calculate that volume, what we first need to do is look at the area. So here's the area that we're talking about rotating. And right away, I would look at this and say, it looks like vertical rectangles would fit into that picture perfectly. All right, so those are all my rectangles. Each one is going to be sitting on my axis of revolution and spinning around. So this rectangle is going to spin around, this rectangle is going to spin around, and they're going to create a bunch of disks. So this is the perfect example for a disk method problem. In the disk method problem, the way we calculate our volume is pi integral from a to b of r squared dx. Dx because I just said vertical rectangles seem to make most sense here. So we have the pi, that's just a given. The a to b is the width. The width goes from here to here. And that's your 0 to pi. R is the height of the rectangles. And the height of the rectangles is changing depending on where I am, but it's always between this curve and the x-axis. So if I did top minus bottom, the function is the top and the bottom is the x-axis, which is 0. So I would just get the square root of sine x. But remember, you have to take r and square it. And that's going to be nice for this one because it gets rid of that square root. So in the end, what do I get? I get pi integral from 0 to pi of sine x dx. Once I have it set up, the integration should be easy. The integral of sine is minus cosine 0 to pi. Then I have pi times negative cosine of pi plus, because it's double negative, cosine of 0. Well, cosine of pi is negative 1, so I'm going to get positive 1. And cosine of 0 is 1. So in the end, I get 2 pi. So the volume of this three-dimensional figure, kind of like a football shape here, would be 2 pi. Here's another one. Find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared, g of x equals 1, about the line y equals 1. Right, so f of x equals 2 minus x squared, very easy to draw, upside down parabola up 2 units. G of x equals 1 would be this line right here, horizontal line. That's g of x equals 1. So first of all, the region bounded by those two things would be this region in here. Again, sort of seems vertical, seems to be the best way to set that up. And then we're going to rotate that around the line y equals 1, which is the same thing as g of x equals 1, so it's around this line. So this is going to rotate down here and spin. Well, all these rectangles here are sitting on my axis revolution. And if I were to spin each one around, I would create a series of disks. And I would fill that volume in. Let's clean this up a little bit. So, what I need to do is the disk method. Well, again, the formula would be pi integral from a to b of r squared, again, dx. Because I said, vertical rectangles seem to make the most sense here in this picture. All right, so we need our width. Our width would be the total width for which this thing spans. So from here to here, I would need to figure out what those values are as it relates to the x-axis. So I could figure out my width on the x-axis. Well, what are they? They're the intersection points between this line and this parabola. So I'll set them in equal to each other. So we got these intersection points. I would get 2 minus x squared equals 1. So what's that going to give me? It's going to be 1 equals x squared. So x equals plus or minus 1. So there's your width. The radius, well, let's fill this in first. Pi negative 1 to 1. Your radius, your r, is really the height of these rectangles. Now we think about the height of these rectangles. The top of the rectangle hits the curve. The bottom of the rectangle hits the line. And so if we do top minus bottom, to get that height, it would be 2 minus x squared minus 1. This is f, this is g. F minus g would get us that distance. A lot of people would just say the function, and the problem with saying it's just the function is you would be measuring from the function all the way down to the x-axis. That's the height you would be talking about. But that's not the height of the rectangle. That's the total diameter of, say, the disk. So that's why we're going to do top minus bottom here again. Again, it's a distance. Think about the height of the rectangle as a distance. And integrate with respect to x, so we're ready to go. So I'll just clean this up a little bit. Negative 1 to 1, this will be, what, 1 minus x squared dx. And so we would get pi times x minus x cubed over 3 between negative 1 and 1. So pi times 1 minus 1/3 minus negative 1, what's that going to be, plus 1/3. Again, you plug a negative into here. Cube is negative, and this negative would actually make it a plus. Don't forget the whole thing's still being subtracted anyway. So we distribute that negative in here, and what do we end up with? We end up with 1, and 1 is 2, minus 1/3, and minus 1/3 is minus 2/3. So 2 minus 2/3, which would give me, so I get 4/3 pi, and there's your answer. Now we move on to the washer method. And the only real difference between the washer method and this method is the placement of the rectangle. In the disk method, our rectangle sat right on that axis of revolution. And when we spun it, we got a solid disk all the way through. In the washer method, our rectangle sits off the axis of revolution. And there's this space in here. And if we were to spin that rectangle around, you would get what looks like a washer that's hollow in the middle. And that's really the only difference between a disk and a washer, is a washer is hollow. And so we would have to figure out how we can find the volume of this washer based off of the measurements of this rectangle. And so we're going to look at a couple of things. So we have a couple of measurements. One is a distance from the axis of revolution to the bottom of the rectangle. We're going to call that little r. Then we have the distance from the axis of revolution to the top of the rectangle. We're going to call that big R. Notice neither of those is the actual height of the rectangle. Okay? I could find the height of the rectangle by looking at those two measurements and subtracting them, but neither of them is actually the height of the rectangle. Okay, so big R, little r. And then the width is still the width or the thickness of the rectangle. So then I transfer that over to the washer. So here's that rectangle still. Here's the axis of revolution. This distance here is little r. This distance here is big R, and we have the width. So if I look at this, what I really have are two disks. Okay? I have this disk in here, which is missing, right? That's the hollow part, but you can think of that as a disk. And then I have this bigger disk that's not solid all the way through, but let's imagine that it is solid all the way through. So if I take this big disk that's solid all the way through and I subtract out the hole, that would give me the washer space in between. So essentially I could find the volume of this washer by subtracting two different disks. Well, the way I do that is by looking at the volume of the disk. So the volume of the bigger disk is calculated by using the bigger radius, so pi r squared w. The volume of the smaller disk, the one that's missing, this hollow spot, is by looking at the smaller radius, pi little r squared w, and then subtracting them. And if I subtract the big disk from the little disk, I get just the ring that is the washer. And I can simplify that formula a little bit. They both have pi in them, so I could factor the pi out. They both have w in them, so I could factor the w out. And so I really have big R squared minus little r squared times pi times w. All right, so that is the volume of one washer. And so once I have the volume of one washer, I got to think about how am I going to create this series of washers added together, and then have all those washers give me the volume I'm looking for. Well, it's the same process as before. If I took the sum of the heights, or in this case, all the washers, which would be pi, I would get my big R squared, my little r squared. That's my w, which we're now going to call delta x, because delta x is the width of the rectangles, and therefore the width of the washers. If I took this and I added this up, what this is representing is adding up all my washers. If I add up all my washers, this should give me an estimate of what the volume is using the washer method. If I then took the limit as n goes to infinity of this, where n represents the number of subdivisions and therefore number of rectangles and therefore number of washers, that should give me the actual volume of a bunch of washers added together. Well, again, this is no different than what we just did a second ago. This will come all the way out to the front. Really what we're looking at is this is just a function. It's two functions subtracted, each one squared, but it's just a function. This width will represent in the integration, and so what we end up getting is one of these two integrals. And so here's your two methods of integration for the washer method. Whether we want to do it with x here, so big R squared minus little r squared, dx, a width represented by the a to b, or we do it with respect to y, same thing, big R squared minus little r squared dy. Remember what r's represent. Big R, axis of revolution to top of the rectangle, little r, axis of revolution to bottom of the rectangle. Okay? So inner radius, outer radius. That's really what we're talking about here. And again, it says horizontal axis of revolution, vertical axis of revolution for the same reason it did before. We looked at the disk method, and that's because if I have a horizontal axis of revolution, I'd have my rectangle sitting here just with a space, but the rectangle is perpendicular to the axis of revolution. So that would create a vertical rectangle, and therefore with respect to x, here I'd have a horizontal rectangle with a vertical axis of revolution. I have this space in here, and I'm going to spin it around this way, creating my washers. So my washer is either going to be created this way, or it's going to be created this way. What you decide depends on how you want to put your rectangles into the picture, but generally you have the same process either way. Okay, let's do some examples. So find the volume of the solid formed by revolving the region bounded by the graphs of square root of x, y equals x squared, and around the x-axis. So each one of these curves, the red curve is your square root curve, the blue curve is your x squared curve, and you want to rotate around the x-axis. So first off, you got to throw some rectangles into this picture and decide how you want to do it. Do you want to do it with vertical rectangles, which we very well could do? If we do it with vertical rectangles, it seems to fit very well where the top of the rectangle is constantly hitting the red curve and the bottom of each rectangle is constantly hitting the blue curve. So vertical rectangles seem to work here. We're rotating around the axis of revolution being the x-axis here. Notice all these rectangles are sitting off of that axis of revolution. Even when we get down to this end here, the curve only finally touches the x-axis at this point. So still, once we move off that point just slightly over here, we're going to be off the axis of revolution. So this is setting up to be a washer method problem. If I was to rotate this rectangle around, I would have all this hollow space inside here, and I would get a washer, and the same thing would go for all of them. So you kind of think about three-dimensionally what the volume would look like. This would rotate down here, right? And you'd have this sort of bowl-looking thing on the outside, and the inside would be this convex center of the bowl. Okay, so again, created by a bunch of washers. So now, if we're going to do this using the washer method, and that's really going to have to be your decision, is this a washer method problem or is this a disk method problem? And eventually you're going to have to ask yourself, is this a shell method problem? So we're going to say this is a washer method problem, and the volume is calculated by pi integral from a to b of big R squared minus little r squared. Each one individually is squared, and we're going to do dx, because again, we said vertical rectangles. So we need to figure out our width, we need to figure out our different radii, and go from there. Well, the width is the width along the x-axis here that we need this figure to span. It starts here, whatever this is, it ends here. So we need to figure out the intersection points between the two curves, so set them equal to each other. Best way to solve that would be to square both sides, so this would become x, this would become x to the fourth. Set it equal to 0. Factor, this would be x cubed minus 1. So I would get x equals 0 and x equals 1. Okay, so I got my intersection points. There's my width on the x-axis. Now my radii. I have my inner radius, which is little radius. This is the inside of the figure. And then I have my outer radius, which is this radius here. And that's to the outside of the figure. So big R, little r. And I got to decide how am I going to calculate those. Remember, they're coming off of the axis of revolution. So the big radius clearly goes to this curve here, which is the square root function. So it's going to be the square root of x squared. I have to square whatever that is. And the little radius is clearly the parabola here. So that's going to be x squared, and I'm going to be squaring that. I take their difference, and I integrate that with respect to x. So what do I get? I get pi integral from 0 to 1 of x minus x to the fourth dx. So now what I need to do is integrate. Very simple. X squared over 2 minus x to the fifth over 5 between 0 and 1. So I get pi times 1/2 minus 1/5. Switch those both to tenths. I get, this is going to be 5/10, 2/10, so 3 pi tenths is going to be my answer. So the volume that we would get of that weird looking bowl would be 3 pi tenths. But the big thing here is recognizing that this one is different than the previous in that the disk method wouldn't get this job done because this is not a solid figure all the way through. And that's really the difference between the two methods, is deciding which one fits the volume that you're trying to calculate. So the hollow inside washer, solid all the way through disk. The thing that they both have in common is that their rectangles are always sitting perpendicular to the axis of revolution. Okay, here's your axis of revolution, here's the rectangles. Now, I could have very easily, I shouldn't say very easily, I could have just as well set this up with horizontal rectangles. If you look at this, it would work. The right side of every one of these rectangles hits the blue, and the left side of every single one would hit the red. Now, if I did that, I would just have to do everything in terms of y. So I'd have to flip these equations around so they're x equals instead of y equals. My width would be calculated along this axis. So I'd have to look at the intersection points in terms of the y values, not the x values. But I could have very well done the exact same thing, found the exact same volume. Again, it would have still been rotated around the x-axis, but the rectangles I'm using to rotate would be rectangles that are set up horizontally. Now the problem with that in this method is that those are parallel to the axis of revolution. So when I try and set it up, it doesn't really fit the washer method because we said our rectangles have to be perpendicular. So from an area standpoint, yes, we could have done horizontal rectangles. But from a volume standpoint, these two methods we're talking about don't allow your rectangles to be parallel with the axis of revolution. That's ultimately where the shell method's going to come in. But that's a little bit further down the road. We'll get to that later. All right. This is what we're going to look at over the next two lessons. So today and then the next lesson. Because we can get this done today using the disc and the washer method. It's just not the best way to do it. The best way to do it is to use what we call the shell method, which we haven't learned yet. So let's look at the problem. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, which is this red curve, it's this parabola. Okay? Y equals 0, which is the x-axis. X equals 0, which is the y-axis. And x equals 1, which is this line. So the space that's bounded by all this is in here. Okay? All right. So when I set that space up, if I just said find the volume, and I didn't say let's look at the axis of revolution at all, just find the area, sorry. If we were just finding the area, I think everyone would look at this and go, yeah, vertical rectangles make the most sense, right? Let's put those rectangles in. The problem is we have to look at the axis of revolution, which is the y-axis. And those rectangles just don't orient the way we want them to with respect to that axis. They're parallel. And both the disc and the washer method, you can't be parallel. You have to be perpendicular. So this tells us we have to put in horizontal rectangles. And this is why just using the disc and washer method is no good. That's why we're going to learn another method that'll give us some flexibility here. So if we have to do horizontal rectangles, we have a problem. First off, you should recognize that if we're doing horizontal rectangles, everything's going to be in terms of y. Okay? But the problem is right here. When I look at this space up here versus this space down here, let's call this area 1 and area 2. The height of those rectangles, the right side and the left side, changes up. In which case here we get the right side and the left side of each rectangle. Here we have the right side, but the left side is this curve now. So to find the heights of these rectangles would be different than the way we find the heights of these rectangles. So I have to calculate each of these areas differently. But if I then look at that and I rotate these around this axis of revolution and these ones around this axis of revolution, I could find the volume of that one, a volume of area 1 rotated, volume of area 2 rotated, and the two volumes combined would give me what I'm looking for. So let's split this up into volume 1, or let's say this one's volume 2, and volume 1. Okay? Volume 1 would be this space rotated around this axis. Okay? Volume 2 would be, or sorry, volume 1 would be this space. Keep flipping it. Volume 1 would be this space, area 1, rotated around the y-axis. And volume 2 would be area 2 rotated around the y-axis. And then I'll combine them. So the total volume I want is volume 1 plus volume 2. Right. Well, all the rectangles in area 1 are sitting right on the axis of revolution. So all of those rectangles in here are disk problems. Okay? As opposed to all the areas in all the rectangles in area 2, these rectangles in here are sitting off of the axis of revolution. We have all this hollow space in here. Okay? So we have to really do this in two ways. This is going to be disk, and this is going to be washer. So you see all these hoops we have to jump through simply because we're forced to do horizontal rectangles, which don't really seem to make sense. If I was drawing this picture, like we said, vertical rectangles would make the most sense, but we can't do that. All right. So if I look at volume 1, and my computer works so you can see this, if I looked at volume 1, I would have pi times the integral from a to b of big R squared dy. Again, dy, right? We have to do horizontal rectangles. That's your disk method. Plus pi times the integral, let's say from c to d, of big R squared minus little r squared dy for the washer method. These r's are not necessarily the same as these r's, so if you want me to use a little bit of different subscript, I'll just use a different color to show you that r is different than, say, this r is possibly different from this r. Let's use a different color here. I can always use subscript, say r1, r2. All right, anyway, let's look at each one separately. Let's do this one first. A to B is the width. The width goes from here to here. This is my width. Okay. This is starting to get pretty messy, so let's erase a lot of this so you can start to see it. Well, the width from here to here is 0 to 1, and that's pretty easy because this, remember, is a parabola up 1 unit, so you know exactly where that starts on the y-axis. So we know we're going 0 to 1. The radius is the distance from here to here. Okay. If remember, this is x equals 1, and this is x equals 0, so that distance, if we did right minus left, is always going to just be 1 squared dy. Done. The other one, we need the width, which is now from here to wherever this intersection point is here. So we got to find this width. So that intersection point would be found to be 2. And the reason is because it's the intersection of this curve and this line, which is this function and this function. And if I were to set those equal to each other, what you would get is that you would get something that doesn't make any sense. The reason is because look what I just did. And this is good. I mean, it shows you things that you got to make sure you watch out for. This is y equals. This is x equals. I can't set them equal to each other. They have to be two y equals equations or two x equals equations. So I can't set them to each other. However, what I can do is I can take this thing, I can plug it into here, and that would give me y equals 1 squared plus 1, which would give me 2. And so you see that the intersection point has a y value of 2. So we're going from 1 to 2. And then we need our radii. Remember, big radius from axis of revolution to the outer edge of the figure, which in this case is actually the same radius that we had down here. 1, square that. You know, it wasn't necessarily going to be the same radius, but in this case it was. And then the small radius is the inner radius, so that's to this curve here. So axis revolution, let me erase some of this now, it's again starting to get messy. Axis revolution, inner edge, this is the radius, okay? So this is little r. So in that case, if I did top minus bottom, in terms of y, I'd have to flip this curve around. So I have to take this curve, y equals x squared plus 1, and I have to write that as x equals. Well, that's easy. It's going to be square root of y minus 1. Subtract a 1, take the square root. Okay. So I'm going to have to do that minus x equals 0, which is the y-axis. So ultimately I just get this. And then I'm going to integrate that with respect to y. All right, so now I'm all set up. Pretty easy integrals to do once I get this set up. So this first one will be pi. Integral of 1 dy would just be y between 0 and 1. Plus, over here I have pi. If I square this, I'm squaring the square root, so it cancels. So let's rewrite this first. I get 1 minus y minus 1 dy. So if I distribute this in, I'll get negative y, and I'll get another plus 1, so 2. So what I end up with is pi times the integral of 2 would be 2y, minus y would be y squared over 2, and that would be between 1 and 2. So here I get pi times 1, after I plug 1 in. Here I'm going to get pi times, 4 minus 4 over 2 is 2. If I plug 1 in and subtract it, I get 2. Then I'll get 1/2 subtracted with the negative, so plus 1/2. And I end up with, really all this cancels, so I get 1/2. So I have pi plus pi times 1/2. Well, that's going to give me 3 pi halves. So the total volume of this whole mess here, rotated around the y-axis, would be 3 pi halves. Now, doing it this way is completely not the way we would ultimately do it. But it's the way we're forced to do it by only knowing what we know. Keep this answer in mind. We will come back to it. I will show you an easier way to do this once we learn our third method of finding volumes, where we'll be allowed to do vertical rectangles. But right now, this is where we're at. It's still done, still doable, okay? But lots and lots and lots of ways around it that we have to go. Here's our final one. This one, most complicated because we have to develop the whole system here for solving this. So what we're going to do here is we have to model what equations would create this situation. So a manufacturer drills a hole through the center of a metal sphere of radius 5. So you have to figure out, how would I create a sphere radius 5? And the hole has a radius of 3. What's the volume of the resulting metal ring? So you can see the picture here, sort of giving you what that would look like. You would get sort of like this bead you would see on a necklace or something with the hole through it. So let's think about how this would come about using areas. Well, the way I would find a sphere radius 5 would be by taking a circle, or even, let's say, half of a circle that has a radius of 5, and rotating that 360 degrees around, say, the x-axis. So if I took this half circle and rotated it around the x-axis, I would get a sphere, right? This would rotate down here, and I would get this sphere. How could I create this half circle? Well, the way I could create the top part of the circle is by using first the circle formula. So x squared plus y squared, my pen, x squared plus y squared equals radius 5 would be 25. And I'm just using x squared plus y squared equals r squared to create that, but that's the full circle. I don't even want the full circle, I just want the top part of the circle. So what I'm going to do is I'm going to solve for y, and what I get is plus or minus the square root of 25 minus x squared. And what that gives me is the top half of the circle. It goes from here to here, and that's the positive square root. And it gives me the bottom half of the circle, which is the negative square root. But I only need the top half, so I only need the positive square root. Okay, so now that we have all that, I'll rewrite that. I don't need any of this. That's the y-axis. So this is y equals the square root of 25 minus x squared. And then I need that whole radius 3. Well, if this is the center, the radius goes this way, and this was radius 5. To get to a radius of 3, I look at this line, y equals 3. If I cut that right through the middle, then all I really have to do is rotate this piece here around the x-axis, and that would create the shape. Well, that's a perfect washer problem. a bunch of washers here. So if I look at all these rectangles in this space, and I rotated each one of those rectangles in that space around this axis, I could find the volume I'm looking for. So this is a washer method problem. So, washer method is pi times the integral from a to b of big R squared minus little r squared, in this case dx, because notice the rectangles that I have here in the picture. Vertical, right? Vertical rectangles. So, the width is from here to here. This is my width. So I have to figure out what that is on the x-axis. And it's not negative 5 to 5, because the radius of the circle is radius 5, which would place this here and here, radius 5. But notice this cuts off a little bit before. So we need to find the intersection points between this and this. So we set them equal to each other. So square root of 25 minus x squared equals 3. Square both sides, you get 25 minus x squared equals 9. So you're going to get x squared equals 16, which is going to give you x equals plus or minus 4. So this is getting messy. My computer's not working right. But anyway, plus or minus 4. So your width is going to be negative 4 to 4. Your big radius and your little radius. Okay? What you need to worry about. So now our big radius would be from the x revolution to the outer edge of the figure, which is this curve here. So that's this. And the little radius is from here to here, which is this line, which is this. So we get square root of 25 minus x squared, that's big R squared, minus 3 squared, which is little r squared, and again it's dx. So ultimately our integral is going to be pi, integral from negative 4 to 4, 25 minus x squared, because I squared the square root, gets rid of it, minus 9, dx, which would give me pi times the integral from negative 4 to 4 of 16 minus x squared dx. Pretty easy integral to do. Once you integrate, you plug in your negative 4 and 4, do your computation, you end up with the answer. In the end, we end up with 256 pi over 3. So we have our disk and we have our washer method. Next thing we need to learn is the shell method, which will make the previous example a lot easier to do and will give us a ton of flexibility when it comes to finding these volumes of revolution. One thing to remember is that the disk and washer method, your rectangle has to be perpendicular to the axis of revolution. Has to be. And so you could look at the axis of revolution and automatically know what kind of rectangle you need to put into the picture. But I like to set up the picture as, what do I think is easier? Vertical rectangles or horizontal rectangles? And then see what happens with the axis of revolution, and hopefully it's the way it needs to be. In the long run, you're going to have flexibility. For right now, disk and washer is all we have.